Okay.
We're going to change the source here. And then I'll just do what we've been doing, which is just... Oh, I hate when this happens because I'm bad at putting this thing up. I don't know why it's so bad. Oh, come on. I believe. There we go. I keep saying it. One Wednesday I'm coming in here and practicing pulling that down. Okay. So, yeah, we saw. I'm in the middle of grading that, so it'll be grading the whole day. So we're gonna go through this, the mole worksheet, conversion worksheet that you did last night. So just kind of go through and see where we're at on this. Were y'all fairly comfortable with this? Do we have any like major concerns on this one?
I kind of got lost in number 6.
You got lost on number 6? Okay, so when we get to number 6, we can focus on it a bit more. Any other like really problems that y'all felt? I heard 5? Maybe I didn't. I'm crazy then. All right, so 6 seems to be like a lot of y'all struggling with 6. Okay, so we'll focus on that a bit when we get there. We're just going to go through and check the rest of these and see where we're at with these. So, how many moles of lead are in 1.50 times 10 to the 12th atoms of lead? What did we get for this?
2.49 moles.
Okay.
So I have a 2.49 moles. Anybody else give any different answers, or is this about what you know?
Mine's scientific.
You put yours in scientific notation for moles? What did you put for yours? Just
It was times 10 to the 34. I don't know if that was right because I don't know.
well, we'll walk through each of these. So you have this. So I think I know exactly what happened with yours, but we'll walk through what Carson did, and I'll show you. I think I'm pretty sure I know what happened with yours. Yeah.
Okay, so I got 2.49 times 10 to the negative 12.
You have 2.49 times 10 to the negative 12. All right. So what I can tell you is that one of these are definitely right. So we'll go through your processes here and we'll kind of compare here. So let's start, Carson. What did you do for yours?
I did 1.50 times 10 to the 12th divided by 6.022 times 10 to the 23rd.
And then you put atoms on the bottom here, right?
Yes.
And moles on
Wait,
the
how
top
did
here.
you get this?
So this setup is right, but I mean, if you're dividing by 10 to the 12th by 10 to the 23rd, are we just going to get 2.49?
No, you're getting. I got a really big long number, but I just have to.
Oh, so, okay, so you got the right number here, but remember, you can't get lazy on the scientific notation, right? So if you get a 0.000000, it's still, those zeros still count because it's, if we're talking about sig figs again, right? So if it has that decimal place, well actually, so those zeros don't count towards sig figs, but they're used as a placeholder, right? It's the same as like saying, again, you have 1 million likes on something. Doesn't mean you have exactly 1 million likes, but you have around 1 million. So the zeros are used as placeholders to show how big it is. In the same sense, the leading zeros, when we're talking about like a really small number, are used to show how small it is. So you can't necessarily skip out on those. So if that's the case, we're going to say that this is wrong. Madison, did you do the same setup here as Carson?
Yeah.
You did pretty much the same setup? Yeah. So this setup is absolutely right. You did the right thing here with the conversion, dimensional analysis conversion here. So you should have gotten 2.49 times 10 to the 12 here. For yours, what you did, you probably multiplied by 6.02.
But I need to do that. Oh my god.
Yeah, that it happens. It's just kind of keeping in track what your number is. Again, remember, what is this number called?
Scientific notation.
No,
Is it like-
Avogadro's number. Yeah, there you go. So again, Avogadro's number is always atoms per mole. If you need to get rid of atoms, you got to move the number to the bottom. Moles, which was on the bottom originally, has to move to the top. So just making sure to keep your dimensional analysis in track and making sure you're keeping track of your units, right? Does that make sense for everybody? All right, awesome. So I'll just show the rest of this. Okay, number 2. How many moles of calcium are in 3.82 grams of calcium? What do we get for this one?
Yeah, I struggle with this one.
Struggle with this one? What did you get, Madison?
We're supposed to say in scientific notation.
If it needs scientific notation, yeah. Which you probably should.
9.53 times 10 to the 24.
So 9.53 times 10 to the what?
Negative 2.
Negative 2.
I got 0.09. It wasn't even like 1 volt, it was less than 1. And I got scared.
Well, I mean, so let's think about it this way, right? So I explained this as like an analogy in class on Friday, but like, so a mole, again, it's kind of just used to represent that number, it's to represent Avogadro's number. In the same sense, like a dozen is used to represent 12. So like you can have a fourth of a dozen, right? How much is a fourth of a dozen? Fourth of a dozen. Dozen is 12?
Fourth a dozen.
Three, yeah. It's all good. So you can have like a fourth of a dozen. In the same sense, you can have less than a mole here, because again, the mole is really just talking about this number. It's used because it's easier to group up moles than 6.022 particles, or times 10 to the 23rd particles. So you can have less than 1. So you got what? 0.09. Did you write anything? You said that's it?
I did 6 figs. I forgot what the actual answer was.
So the sig figs here would be 3 sig figs. So if you're going to do this for sig figs, how many do you need to put this out to? Because remember, are these significant or no?
Oh, they are leading zeros.
Yeah, leading zeros. Leading zeros is never significant, right? So what you probably ended up getting is this. So I think you got the right answer here. It's just that you didn't write it in scientific notation, which again, is fine whether you did so or you didn't. It's just as long as we're keeping track of those sig figs, as long as you have the right answer. And for answers like this, there's not too much, so you don't necessarily have to write scientific notation, but if it's more comfortable with you to keep track of sig figs, you can. On longer answers, like if this had like 6 leading zeros, then you're probably going to want to do scientific notation because it's a little more convenient to do that over writing 10 zeros and then your number. Like for this answer, for example, you would not in any world would want to write out 11 zeros in front of this 2. That would be miserable, and that's why one of the reasons why we use scientific notation, right? So we got 9.53 times 10 to the negative second, or 0.0953. Both of these are right. It's just that this is written scientific notation up here. I was going to say any other answers, but I just told you I was right anyways. But does everybody agree with this? Did we get a different number for this?
I don't understand how they all got that.
Okay, then let's talk about it. So, Madison,
Yeah.
you gave me the first right answer, so let's talk to you here. So, yeah, 3.82 grams, right? And so how did you set this up? How did you get from 3.82 grams to, make sure this is moles. There you go.
I had 3.82 grams times 1 mole over 40.078 grams.
40 point what?
078.
078. Yeah, that's it. Okay. So that setup works there. So what is this number, 40.078?
Atomic number of calcium.
Not the atomic number, but
Mass.
the atomic mass. Yes, the atomic mass of calcium. Yeah. So basically the problems like this, again, you can kind of use the conversion little cheat sheet up here. When you're going from grams to moles, you use the periodic table, you look at that atomic mass. Because the periodic table has the, which I guess is a little disingenuous, the atomic table has the average atomic mass on it, but I mean that's what we use, because if we're talking about just calcium, it's not like they gave us the isotope and gave us the atomic mass of that isotope. When we're talking about calcium, we're talking about the average calcium. So we use the periodic table, use the atomic mass on the periodic table, and that gets us a gram per mole. Because again, 1 AMU is equal to what?
1 mole.
1 mole.
1
Calcium.
gram per mole. 1 gram
Gram
per
per-
mole. Yeah, you're good. And so it's useful as a conversion sheet. You'll use it a lot, so I know it's a little confusing. It's just getting used to it. Remember that 1 AMU equal to 1 gram per mole. Honestly, you really don't use AMUs at all. I'll be real with you, especially when we go further into chemistry. So really, when you look at the periodic table, I know it says AMUs, but really you just think of them as gram per moles when you're talking about atomic mass. It's just way easier. You don't have to worry about converting this, even though it's the exact same conversion. and AMUs in general. I think I mentioned they're like 1 point something times 10 to the 24th, negative 24th grams. So AMUs are going to deal with, and that's why we just use grams per mole, because again, we can convert between it. So yeah, that's essentially the setup. We use the, like Madison said, we use the atomic mass, we set it up like this, grams cancel out, and we get our answer over there, the 9.53 times 10 to the negative second mole. Alright, I'm going to check what time it is, because if we have enough time, I'll go through the rest of these, but like 3, 4, and 5 are the exact same, just using different elements. Let me, my phone's over there, no!
So 123.
121.
121?
20 minutes.
So we got about 20 minutes?
I watched part off, but
Let's do
124.
one more of these problems just to see where we're at, and then we'll skip over to the last 4, because those are the ones that are a little bit difficult, and then we'll have a little bit of time left to see where we are on these fill-in notes to see if we're comfortable with them and filling them. So, number 3, compute the number of moles of copper, and 2.4 times 10 to the negative third grams of copper. So, what did we get for answers on this one?
I got 3.8 times 10 to the negative 5.
You said 3.8?
Yes. 'Cause It
3.8?
used to be 3.7, but I rounded it because it had two
Gotcha.
sig figs.
Any other answers for this one?
I did 3.78 times 10 to the negative 5.
So you just carried it out to 3.78?
Yeah.
Okay. And then anybody else know? So yeah, that's right. Oh,
yeah, I got 3.77.
you got 3.77. So again, let's talk about sig figs here. How many sig figs are in this number?
2.
So how many sig figs should be in this number?
2.
Exactly, yeah. So 2 sig figs is right. Being within 1 digit there is fine. Like if you put 3.7, it would have been fine. Because it's like,
that one was like 2.4. I was like,
yeah, like again, we're talking about this, again, like, if we draw this out, 1, 2, 3, 4, 3, 7. One digit in the difference between this number, especially depending on what you're dealing with, like what we're dealing with, like moles here, that's a really small number. So like being off by just that much is perfectly fine. It happens, especially with rounding errors. You know, it just all it depends. So that's completely fine. 3.8, 3.7, about the right answer. So already asked Madison how she set it up for the second problem. So who wants to give me how they set it up for this problem? Cooper, you got a right answer. So let's see what you got.
2.4 times 10 to the negative third grams is parentheses 1 mole over 63.546 grams.
It's 53.5.
63.
63.546 grams. Yep, looks right. And you just did a parentheses there. I'm used to doing it like that just because it's easier for me to organize it. But yeah, basically it's just the same thing. You just multiply through.
Yeah.
So what he ended up doing is just, yeah, it's basically what you would see in like on math problems.
Mm-hmm.
And so that's fine too. Like, I mean, it's whatever works for you essentially on these, just as long as you're making sure you get those units right. And that's how you end up getting to this number. Does that make sense for everybody? Make sense? We good with this? Cool, awesome. So yeah, let's skip over to number 6 here, because I know a couple of y'all said that 6 was the problem for y'all. And so conversely, we'll kind of go over 7 that way. Because 6 and 7 are pretty much the same as well.
What was the answer number 5?
Answer number 5? Okay, what was that? See, I wish I had an answer sheet on it, but I don't. Oh, so number 5, ooh, actually, let's do that one together, actually, because this one's different. This one's just a double conversion problem here, so let's see here. Who got an answer for this that they're comfortable with? Because if not, we can work this problem out together.
I got 1.330. I don't know if the sig figs are right.
got 1.330 atoms.
Yes.
Is that realistic for 313.2 grams of potassium? Yeah. If one atom weighed that much, we would be, like, bananas would be deadly. Like, bananas would weigh so much, it'd be wild. I would never want to carry around a banana ever. Any other good attempts on this one? No?
It's their own citrix, but I got 4.82 times 10 to the 21.
You got 4.18?
82.
82 times 10 to the what?
24.
24? That seems a little bit more reasonable. Let's go through this together because it's a little uncertain here. So let's start setting this up here. So 313.2 grams here. So atomic mass of potassium, what is it? What do we get? Should we look at the periodic table?
39.093 grams.
It's 39.093 grams. Do we need that on the top or the bottom here?
Bottom.
Bottom, right. Awesome. He said 39.093, right? Am I crazy?
0983.
0.983. Ah, okay. Now, we got to get to atoms, right? So how do we get from moles to atoms? 6.02 times,
10 to the 23rd.
which is known as
The avocado.
Avogadro's number. Don't worry, we had somebody else say Avogadro's number in the last class. I get it. So Avogadro's number. Average atomic mass is what we're using on the periodic table. Avogadro's number is basically telling us how much is in a dozen, except that we're talking about moles and atoms, right? So it's like, 12 digits in one dozen. Compared to 6.02 times 10 to the 23rd atoms in one mole. So just keeping that in mind. And again, looking at, you can use that kind of chart on the top of the cheat sheet. So we have Avogadro's number. Does Avogadro's number need to be on the top here or on the bottom?
Bottom.
Bottom. So 6.02 times, I'll just use 6.02. I mean, are y'all using 6.02 or 6.022?
I said
I'm using the 3-digit.
The 3-digit one? I think the one we give you in the notes is the 3-digit one, but yeah, I think technically you can use the one of the 4 digits as well. But we'll use the 3-digit one just for the sake of keeping things in the same vein as your notes. So again, units on the bottom here, what's the units on the bottom for this one? Not mole. Yeah, no, atoms are right, yes. Be a little more confident, you got it. Atoms right here. Again, because again, Avogadro's number is atoms per mole, right? So if we're trying to get to atoms and moles on the top here, we've got to flip it. No, wait, what am I doing? Wait a minute.
Would atom be on the
Wait
top?
a minute. No. Yeah, atoms is on top. So where should this number be? I was totally going along with this. Where should this number be? On the top? Yeah, it should be on the top, right? Because again,
Okay, this is where it was. This is all where.
I kind of went through the motions there. That's on me. It happens. Yeah, atoms should absolutely be on the top here, right? Because this conversion rate is just atoms per mole. Now, if we were trying to get if we had atoms and we're trying to get the moles, then we would put Avogadro's number on the bottom, right? Because basically, remember, we're just trying to, if we put the main number on the bottom, we're essentially flipping the sign, or flipping the conversion factor, right? So on the top is the normal sign, atoms per mole. If we've got to put it on the bottom to cancel out units, we've got to make sure that the units are in the right place there. So when we do this, grams cancel out, moles cancel out, and we're left with atoms, right? So is this the setup that you ended up using, Madison, or
Yeah.
you did? Okay, so it should be 4.82 times 10 to the 24th. So try putting that in your calculator, see what you get. Again, you're making sure to keep in track, especially with your Avogadro number here. Try to put this in parentheses on its own before multiplying it, because otherwise you might get, it shouldn't matter too much in this case. But just to keep everything in line if you're still having trouble putting it in. Did we get that? Did we get close to that when we're typing in a calculator? Yeah? Alright, do you understand how this works?
Yes.
Good idea? Kinda? Gonna kinda there. What kind of?
I feel like I could do it again. Like, I don't think I could do it by myself right now.
Gotcha. I mean, we can always, I think there's some, is there a problem in the notes? I don't think there is. There should be problems in the study guide. So, I mean, if you need to, this will obviously be video recorded, so if you need to try to do those while watching the video, just try to get more uncomfortable on your own. I would definitely suggest doing that. Just remembering, again, if you want to use that conversion thing on the top here, right? Just to give you a little bit of guide, just to help out. If you're trying to get the grams from moles, you need the atomic mass on the periodic table. If you're trying to get from moles to atoms, you need Avogadro's number, 6.02 times 10 to the 23rd. It's just knowing which units are on top and which units are on bottom here. For Avogadro's, atoms on top, moles on bottom. So if you need to flip it, you have to make sure you flip those units. For average atomic mass, grams on top, moles on bottom. If you need to flip those units, you flip those units. It's all just about canceling out the units to get what you want right here, right? Because we had grams, we need to get to atoms. We know how to get to moles, so we got the moles, and we know how to get to atoms from moles, so we just basically did it as just a two-step process. Any sense for everybody on this one? Okay, so let's go on to number 6 here. All right. What is the molar mass of sucrose? How many molecules of sucrose are in 468.4 grams of sucrose? So let's start with this first part, finding the molar mass of sucrose. So how do we think we can find that? Do we have any ideas on how to start finding that?
So I wrote notes, and then I don't think I wrote it like everything down because I was like, is this even right? Because I ended up getting 28.91 grams per mole for the molar mass, and I was like, I don't know if this is not right.
I think I might know what you did, and what you did is you added carbon, hydrogen, and oxygen's atomic mass together, right? So that is partially correct, right? So if you just did that, we've added 1 carbon, 1 hydrogen, 1 oxygen together, right? How many carbons does this have?
Oh, 12.
12. So what if we added 12 carbons, hydrogens? That's 22 in the middle, yeah. 22 hydrogens, and then how many oxygens right here? 11, right? So 11 oxygens together. So this thought process is right, Taylor. It's just that you got to make sure that you look at how much of each element you actually have, right? So like adding them together is definitely the right choice here. It's just you got to make sure that you account for all the elements in there. Because again, let's take a look at that sucrose. Did I bring it up here? No, I didn't bring it up here. But if y'all remember the video, I think I showed y'all in class too, that sucrose has a ton of carbons and hydrogens and oxygens kind of all in that one molecule together, right? So they're functionally, in order to get the molar mass, you've got to add them all together to get like your total molar mass of the whole thing, right?
Yeah.
So when we add that together, what do we get?
342.297.
342.297. Yep, that's about right. I think on one of the problems that I gave you, I already gave you the mass of sucrose, so just 300. I gave you as 342.3, and that's just rounded up, but obviously with doing the math by yourself, you're going to get a number like this. And of course, again, it'll all be accounted for once you go through and get rid of the sig figs and whatnot. So, because at the end of the day, we're still going to have 4 sig figs. So, and again, the units on this is what? Grams per mole. There we go. All right. So that's problem 1 done. Part 1 done, and now we need to figure out how many molecules of sucrose are in 4.68.4 grams. So we're starting with 468.4 grams. So can we jump from grams to atoms? No, exactly, but we can jump from grams to where? Moles, all right? And so how do we do that?
1 mole is 342.297 grams per mole.
So 1 mole of sucrose is 342.297 grams of sucrose. Remember, this is a ratio, right? So it's like 1 mole of the same substance. And again, we're talking about sucrose here. It really just depends on what you're doing here. And so normally I don't include those in calculations just because it's annoying to write it all out, but it's important to remember that when we're dealing with substances like this, just like keeping in mind that these are grams per mole of sucrose, so it's a ratio that we're using here. So if we're doing this, are we putting sucrose on the top? Are we putting this big number on the top or the bottom? Bottom, right? Because we've got 342, but we know that 342.297 grams of sucrose is equal to 1 mole of sucrose. We're just going to write out sucrose because I don't want to write out this. And again, we have 4.68.4 grams of sucrose. So, we do this, we can cancel out these and we get our moles of sucrose, right? And so we need molecules, right? How we can get from moles to molecules?
The
Avogadro's number, yeah. It's all good. If it's easier to remember as avocado number in your head, just make sure to correct yourself as you're saying it, you know? Yeah, I know. Making sure to say Avogadro's number, because sometimes, you know, just keeping our names in check. I feel bad for Avogadro, you know, we kept calling him avocado, you know?
His name should have been Bacon. So much easier.
His name should have been what?
Bacon.
Bacon? Should have just been bacon.
I will remember that.
Oh, yeah. Nah, unfortunately you can't choose our names back in the day, I guess, so. Especially our last names. So, if we have Avogadro's number, where are we putting this, on the top or the bottom?
Top.
Top. Why? What's the units on Avogadro's number?
Mole.
It's a ratio.
Gram per mole, so you gotta cancel out the.
That's atoms per mole, there you go. Well, in this case, molecules per mole, right? Because we're basically talking about any particle with Avogadro's number. Like I said, with like the dozen example, you know, 1 dozen of donuts is 12 donuts. 1 dozen of marbles is 12 marbles. In the same sense, if we have 1 mole of donuts, we would have 6.023 times 10 to the 23rd donuts. Or if we have 1 mole of marbles, we would have 6.02 times 10 to the 23rd marbles. So it's all about what you're talking about here. So again, we're just counting here. So again, we've got 6.02 molecules here, or 10 to the 23rd molecules over 1 mole of sucrose. So we cancel that out, cancel this out. And we're basically left to do the math on this side. I don't have the math on me, but if y'all want to type this into your calculator and give me an answer, go from there. I want to 140, so you have like 5 minutes.
8.237
Times 10 to the 23rd.
So everybody get this, or do we get different answers here? We're good on this one? Okay, yeah, and those are the right significance. I mean, again, look, we're dealing with 4 here. 4 is our max. Well, technically it'd be 2 with Avogadro's number here, but I mean, if you use 6.022, then it would be 4 sig figs. I mean, it really just depends. So if it was 3 sig figs here, what would we round this to?
8.24.
8.24, right? So generally, we're going to use Avogadro's number with just the 3 sig fig version. So just keep that in mind. The 6.02 is what we generally use for Avogadro's number. But yeah, does this make sense to everybody? How we got here, how we got to the molar mass? All right. So yeah, if you ended up getting 7 wrong, I suggest trying to go back through and trying to do 7. Because 7 is literally the exact same thing as this problem right here, except it's just a different molecule. We're dealing with calcium carbonate here, sucrose here. It's the same exact process though. So give this one a try on your own if you didn't get this. Definitely will help you kind of understand it a little bit better.
So the calcium and the carbon, they're both 1, right?
Yeah, so there's 1 calcium, 1 carbon, 3 oxygens, right? So again, it's the same kind of thing as we did up here. It's just making sure you keep track of how many atoms of each in order to get your full molecular mass. All right, real quick, we're gonna go over something that you can see on, there we go. Okay. So, we'll just go through the process of this. We did this in class Thursday, but let's talk about number 8 here. And if you didn't feel comfortable with number 8 or number 9, I suggest doing number 9 on here. So again, what is the average atomic mass of silicon given the following abundance information on the isotopes of silicon, right? So what do we end up getting here?
9.4055.
What was that?
9.4055.
9.0495.
I did not do that.
9.40.
I got
What'd you
9.32.
Any other answers on this?
It was 9.40.
9.40.
55.
Oh.
Now, do these seem like an average
No.
for these numbers? No.
I did, I got like 200 something, I was like, that's not.
That is definitely not an average.
No.
So let's talk about how we calculate this. Again, so basically when we're talking about abundances here, there's 2 ways to go about it, but the simplest method to me, and I saw a couple people set this up, but I think what happened is they divided by 3 afterwards. So yeah, so we have the 28.110. We know that there's 92.21% of this, so we can multiply by 0.9221. And then we can add that to our other abundance, 29.003. Multiply that by 0.0470.
Oh, no, I did wrong.
And then
I thought I did
multiply
wrong,
this
That's what
number.
I did.
I multiplied it, but I didn't make it less than 1. I just kept it as 9.
So if you kept it like that, the other way that you could, if you didn't convert it from percent to just normal numbers, the other way you could go about it, in order to catch that, is just to divide by 100 at the end, right?
Oh, I did. So was the correct answer 28.1?
That sounds about right?
Yeah,
Like, what did you get, 28 point what?
You can always check your answer about the periodic table.
Yeah, so you got 28.153.
It's a red number on the periodic table.
So yeah, we can look at the periodic table, and we see that silicon is right here. We got 28.0855, so that's fairly close to it. Honestly, this number is weird because given the data that we have on here, this number wouldn't happen because it's like, you know, you have 20.08 and then the highest number on this is 20, or lowest number on this is 20.110. But it's around silicon. So yeah, this is actually absolutely right for this problem. Yeah. So again, the other way, what Taylor ended up doing is instead of putting these out of percents, she did the calculations like this. We just moved these decimal points back.
Yeah, so
And then at the end, she divided by 100 to calculate that. So you can do either or. Again, I know average atomic mass seems confusing because it's like, oh, it's the average, just add everything up, divide by the number of things there. But when we're talking about average atomic mass, again, we're talking about like abundances here. So you're not really dealing with even percentages of each. So it's really kind of going through and making sure you have represented how much of this isotope is in the entire average there, and that's what we use these percentages. So yeah, either or was right there. For the notes, if you are having problems with filling the notes, we just posted a Chapter 3 PowerPoint online. So I'd go through that. If there's anything that's you've been caught up with on the notes, I would go through the PowerPoint, try to fill it out using the PowerPoint. Besides that, you also have the study guide that's due by Friday. Is it Friday or Sunday? No, Monday.
Sunday night at midnight.
Sunday night at midnight.
We're ready to go over it
We'll
all.
go on Monday. Yeah.
Test is Tuesday.
I'm not gonna be here Monday, can I just watch the video?
Yeah.
Yeah.
And speaking of which, why don't we hit stop on that video?
Yes. Oh, thank you so much. I appreciate that.